All right, guys, today we're going to talk about something brand new, something that is extremely important to chemistry, and it is known as the mole. So, the mole is a unit of measurement. It is a unit of measurement just like a pound or an ounce or a gram or a kilogram or a liter or an inch. It's a way of measuring something, but specifically that something is substances. So if you recall from the beginning of the year, we said there's two types of pure substances. There's elements and there's compounds, okay? So in this image, you have an element. Let's see, pen marking. So you've got elements right here: copper, lead, mercury, sulfur. So these are all elements off the periodic table. Now, when elements are combined in a fixed ratio, the other particle type, that is the more complex form of a pure substance, is a compound. So these are this sodium chloride, you've got this potassium chromate, you got some sort of sugar. This is probably, it's not glucose, maybe fructose, or that looks like regular sugar, so it's probably what it is, table or kitchen sugar. Water. Okay, so these are all pure substances. So they are either elements or they're compounds. Okay, so a mole is a unit of measurement that we use. Let me see if I can get this to go away. Hold on. All right, I fixed it. All right, so a mole is designed to measure chemical substance. All right, and we'll talk about why it gets like why elements and compounds get a special unit of measurement. But first, let's take a look at our different chemicals that we have here, okay? So you have, so I'll take lead, for example. Lead, so right here, lead is Pb on the periodic table. So I'm going to tell you guys that it's really important that you guys keep a periodic table handy. Speaking of which, I need to get mine. All right, so I provided a periodic table on here, and I want to first say it's really important that y'all notice that the average atomic masses that are right here underneath each so each of your elements have already been rounded to the nearest whole number. So this is going to kind of be excellent for us to talk about molar masses, like that is the mass per mole of each element or chemical. All right, so this right here is important, okay, because these are just those decimals that are normally on the table that have been rounded to the nearest whole number, so it's going to make things easier. All right, so I was talking about lead, so I'm going to go back to talking about lead. So lead right here, this is 1 mole of lead that's in this dish, okay? So in this evaporating dish is 1 mole of lead. In this evaporating dish is 1 mole of copper, okay? So we're going to talk about what that means. So 1 mole is equivalent to the mass of that element, okay? So we use the average atomic mass from the periodic table. So if I find lead, all right, so lead is right here. Now, the one thing about this table I don't like is that it doesn't provide the actual names. I know the symbols, but you guys have a copy in your binders that I've given you. And there's also, it's still available in Schoology, another copy of the periodic table, but it'd be best to use a table that has the element listed for you guys, since you guys aren't familiar with the symbols, or not all of them at least. So number 82, Pb, is lead. Now, this number right here is the average atomic mass rounded to the nearest whole number. Now, the reason why this is important is because if we're saying that all of these up here, all of these different, and I've got some of them covered now with my periodic table, but all of these substances, if that's 1 mole, how do we know? Like, how do you know how much 1 mole is? Well, when we look at the table, that average atomic mass is the amount in grams that represents 1 mole for that element or that substance, okay? So what I'm saying is that lead, that is 1 mole of lead, which is Pb, all right, is equal to 207 grams, okay? So that's because the atomic mass units, so basically if 1 atom of lead has a mass of 207 atomic mass units in its nucleus, it weighs a 207 grams in realistic day-to-day life. Now, I say realistic day-to-day life because we cannot measure individual atoms and molecules because they're much too tiny. So this number, 207, is the amount of grams in 1 mole of lead. So over here, if this is truly 1 mole of each of these substances, this is 207 grams of lead, okay? Copper is Cu, that is its, so 1 mole of copper is equal to, so if I find copper on the periodic table, remember this is the atomic number, okay? This is the atomic weight, okay, the mass, which we are now learning is the molar mass in grams. So it's the amount the substance weighs in grams per mole, okay? Now, so copper weighs 64 grams per mole, okay? Now, I want to take a look at some of these other substances. Right here, this is sodium chloride, which is regular table salt. It's a compound, not an element, all right? But it's still 1 mole, okay? This sodium chloride, this in this dish is 1 mole, okay? So how much does it weigh? Well, 1 mole of sodium chloride, okay, is simply the mass of those elements combined. So if I go to the periodic table and I find sodium right here, and I find chlorine right here, I'm going to go ahead and erase the other two so they're not confusing us, okay? So we can kind of pinpoint and target these two. So I've got sodium and chlorine. That's what sodium chloride is. So all I have to do is take the 23, which is the mass per mole of sodium, and add it to the mass per mole of chlorine. So 23 and 35 is 58. Grams, all right? So 1 mole of sodium chloride is equal to 58 grams of sodium chloride, okay? Now, I want to bring back something that we talked about earlier this year, dimensional analysis. This is going to be something that we practice on and use this stuff with, all right? So if you didn't have an opportunity to master it a month ago, you're going to have that opportunity now, all right? Because we're kind of getting into the early stages of stoichiometry, okay? So we've got to learn how to like measure out chemicals and use conversion factors with them. So each of these up here that I have, that we've looked up using the periodic table, each of these are conversion factors, okay? So meaning that we're going to use these in dimensional analysis, all right? So you've got 58 grams of sodium chloride here, and then this was 64 grams of copper. So we could go through and do this for each one of these, all right? Now, it would take some time, so I'm not going to go through that and do that, but do know that you are able to determine what we call, now, these up here, these are what are known as the molar mass. So molar mass is simply the grams per 1 mole, okay, of a substance. Now, you see this right here. This is the abbreviation for a mole. I know it doesn't seem like much of an abbreviation, but that's it, okay? Because M is taken by meters, it's taken by milli, so we don't use just an M. We either write out the whole word, M-O-L-E, or we put M-O-L. I like to always write the L capital because an lowercase l looks like a 1 to me. So it's the amount, molar mass is the amount of grams for whatever that chemical is per mole, all right? And that's exactly what we were doing over here to the right over here. So the molar mass of copper is 64 grams per mole. The molar mass of sodium chloride is 58 grams per mole. All right, now I'll do one more just for the sake of it. So right back here, you can't see, but inside of this beaker is water, H2O, which is obviously a very common substance for us. So water is H2O. So 1 mole of water, H2O, would be, so first of all, that is, and I just wrote my O really small for some reason. All right, so the 2 indicates that it's 2 hydrogens and 1 oxygen. So that means we're going to take 2 of these and then 1 of these, all right? So, excuse me. So that's going to be hydrogen, which weighs 1, but there's 2 of them. So that's 2 times 1. So it's 2 times 1 plus the oxygen, which weighs 16. All right, so because there was 2, again, let's not lose track, because there's 2 hydrogens, you have to multiply by the atomic mass, which is 1 twice. All right, plus oxygen, which we've only got one of those, 16. So that's a total of 18 grams. So 1 mole of water is 18 grams of water. Now, the reason why this is so important is because this allows us to be able to make it relative to us in the lab. Like we can, so now when I tell you, hey, Brianna, I need you to get 1 mole of magnesium, she knows now what to get, okay? Here's magnesium. She knows if I go weigh 24 grams of magnesium, that is, I take 24 grams out of the stock bottle and put it on the electronic scale, that is 1 mole of magnesium, okay? Moles are important. You need to be able to measure out moles, and here's why. The reason why we have to know what a mole is because eventually we will balance chemical equations, and for a scientist in a lab, in order to create new substances, you have to have mole quantities, okay? So let me show where the mole quantity is. So you see this 2 in front of the hydrogen gas, this 2 in front of the water. Over here we have a 3 in front of hydrogen gas. We have a 2 in front of ammonia, all right? Those are mole quantities. So it's basically like being in the kitchen. If you need 2 cups of water for every 1 cup of pancake mix, that is your ratio of ingredients. Same thing for chemical reactions. So right here, it's telling you that 2 moles of hydrogen gas are needed for every 1 mole of oxygen gas. Now, see how there's not a 1 right here? It's just like in algebra. You don't need a 1 right here. It's understood, okay? So there is an understood 1, so I'll go ahead and put that there. There is an understood 1 right here in front of the oxygen gas, but it doesn't have to be written. Actually, it's quite weird if you did write it, all right? So what it's telling you is that 2 moles of hydrogen gas for every 1 mole of oxygen gas will give you or create or produce 2 moles of water, okay? That's why. Because we can't actually say, hey, let me go get 2 atoms of 2 molecules of hydrogen gas and 1 molecule, because you can't pick out. We cannot manipulate individual atoms and molecules. They're much too tiny. But we can determine how much a mole is, just based on the molar mass that we were determining from the periodic table. So over here in this reaction, this is the synthesis of ammonia, okay? It's a common household cleaning product, all right? And it's saying that there's an understood 1 here, like I just said. It takes 1 mole of nitrogen gas for every 3 moles of hydrogen gas to create 2 moles of ammonia. This is the ingredient list, basically, for creating ammonia. So all chemicals, all right, so you have to understand how important this is to pharmaceutical labs, anything that basically is produced in industry and sold on store shelves, okay, whether it be pharmaceuticals or consumable goods. At some point, some sort of chemical reaction was created to actually produce that new substance, and new substances are being synthesized all the time. All right, so you have to have these mole quantities. So I know if I need 1 mole of nitrogen, that I can go to this periodic table and know how much that is in grams, okay? So if I go over here and I find nitrogen, all right, nitrogen has a mass, an atomic weight of 14. Well, right here, that 2 means that it's 2 nitrogens, all right? So that means that 1 mole, if I'm needing 1 mole of nitrogen gas, which is N2, all right, then that means I'm going to need 28 grams of nitrogen, okay? So, and that is based on its atomic mass, and it's 28 because all I did was take 14, which is that mass, okay, and multiplied it by 2, okay, because there's 2 of them. That's what that subscript means, is it's 2 nitrogens combined, all right? Now, if I needed 3 moles, okay, so if I go over here and I find hydrogen, okay, hydrogen gas is 2 hydrogens combined. So that's 2 hydrogens times 1, which is the atomic mass, equals 2. So 1 mole equals 2 grams. Okay, this is of hydrogen gas. All right, so if I need 3 moles, I'm just going to say 3 times 2, which is 6. Okay, so what we're doing here is what I'm doing here is I'm kind of jumping ahead just to show you guys the application of this. Why are we learning about a mole? Because it turns out when we balance chemical equations, that is, whenever we go into balancing chemical equations, there is a purpose to it. We are ensuring that we have equivalent amounts of substance on both sides, and then we can use those mole quantities, that is that coefficient, right? So you can see it's called coefficients. Those coefficients are the mole quantities that we can actually measure out in a lab type setting. Okay, so we've learned that 1 mole of any chemical substance is directly equivalent to its atomic mass on the periodic table in grams. Now we're going to talk about the mole in terms of a count, okay? So where did this number come from? Okay, so first of all, the mole itself represents a really big number. Okay, so for example, let me go ahead and just use an element that we've already talked about, which is copper. Okay, so copper All right, so copper has a rounded average atomic mass. So if I look at the periodic table, it has an average atomic mass of 63.546, but I can round that. This is 64. So 1 mole of copper is equal to 64 grams of copper, which is equal to 6.02 times 10 to the 23rd atoms of copper, or particles of copper. All right, so here's what this means. All right, atoms and molecules are extremely tiny, so technically if I wanted to measure out copper, all right, I have to do it in grams. I can't actually count out 6.02 times 10 to the 23rd atoms of copper. Same thing. So this is kind of like a dozen. So like, all right, so I don't want to lose you guys. So let's say I have 1 dozen donuts, right? That's 12 donuts. If I have 1 dozen eggs, that's 12 eggs. If I have 1 dozen cars, that's 12 cars. Well, when it comes to 1 mole, same thing. 1 mole of magnesium is 6.02 times 10 to the 23rd atoms of magnesium, okay? Which weighs, and again, I'm just showing how all of these are equal to each other. Magnesium's average atomic mass is 24 grams of magnesium, okay? So 1 mole of anything is going to be equal to this many particles of that something, okay? If I have 1 mole of water, and I could still write this the same way. I could say 1 mole of water is equal to 6.02 times 10 to the 23rd molecules, which you can just say particles, okay? So molecules of H2O, or water, which is equal to, in grams, we already added this up. If I look at the periodic table, hydrogen weighs 1. That's 1 plus 1 plus oxygen is 16. We already looked this up earlier. 18 grams of water. Okay? So 1 mole, no, excuse me, I just messed that up. 1 mole of any chemical substance that is an element or compound. Now, you can see right here, it says atoms, molecules, ions, or electrons. We're really just going to be talking about atoms and molecules. You guys don't have to worry about this. But anytime we're talking about an element or a compound, which is atoms or molecules, we are talking about we are talking about this mole quantity, which is a really, really, really big number, okay? And we'll talk about how big this number really is in upcoming days as we go into this a little bit further. Okay, so let's wrap this thing up and connect the two things the one thing concept that I just introduced to you, and then the whole idea of molar mass that we started talking about. All right, so we'll wrap all this up, and then we'll be able to practice with it as the week goes on. So right here, inside this beaker, is 1 mole of water. Okay, 1 mole of H2O. Same thing for all of these. In each one of these evaporating dishes, in this beaker, in this flask, okay, is 1 mole of each of these individual substances, an element or a compound. The mole concept is only used on on elements or compounds on pure substances. All right, so this is 1 mole of H2O, which is equal to, as we looked up earlier, that is equal to 18 grams of H2O, all right? And that is 6.022 times 10 to the 23rd particles of H2O. In this case, this would be molecules, okay? So if it's a compound, it's molecules. If it is an element, it's atoms. So there are 6.022 times 10 to the 23rd molecules of water in this flask, which is a huge number. It weighs 18 grams. That's 1 mole. Right here, this is sulfur. It's an element, okay? 1 mole of sulfur, and so sulfur is the element symbol is S on the periodic table. 1 mole of sulfur, that is, its average atomic mass is 32.064, so that means that it is 32 grams. So 1 mole of sulfur weighs 32 grams of sulfur, which would be 6.022 times 10 to the 23rd particles of sulfur. Now, instead of putting particles, we can be more specific, okay, for each of these. This is going to be atoms, okay, of sulfur. This is going to be molecules of water, because water is a compound, okay? So remember that the count is always that, what we call Avogadro's number, or Avogadro's constant, which is 6.02 times 10 to the 23rd, all right? And that's how many particles it is, whether it's an element or a compound, okay? But the mass is subjective. The mass depends on its mass from the periodic table. Just like 1 dozen eggs is 12 eggs. 1 dozen donuts is 12 donuts. But do they weigh the same? No, okay? So same thing with chemical substances. Each of these substances we see pictured here have 6.02 times 10 to the 23rd particles in that sample, but their mass, their weights are different. Their weights are subjective based on their atomic mass from the periodic table. So, last thing I'm going to leave you with, okay? If I had 2 moles of sulfur, all right? So if I have 2 moles of sulfur, right? How much would that be? Well, we would just double our numbers. 2 moles of sulfur would be 64 grams of sulfur, right? Because that's 2 moles. Since 1 mole weighs 32 grams, I would just double that. That'd be 64, okay? And that would be double this number. So I could take this number and say 6.022 times 10 to the 23rd atoms of sulfur, times it by 2. That's how many particles of sulfur I have, okay? So we're going to be using molar mass and this constant, this Avogadro's number, throughout the week this week.